most chemical reactions, instead of going to completion, will establish something called equilibrium, where the reactants and products exist together in the system and are balanced, like a scale, with reactants on one side and products on the other. Now, this is all well and good, but what about when something happens that unbalances the scale? How will the system react? This is where Le Chatelier's principle comes in. This principle governs how the equilibrium of a system will react to certain changes. One such type of change is a change in concentration. When more of a reactant or product is added to a system, the concentration of that species increases. On our scales, we can think of this as making that side of the equation heavier. In order to balance out the scales again, some of the quote-unquote weight must be transferred to the other side. If the concentration of a reactant is increased, this happens through the equilibrium shifting towards the products, meaning that more products are made. The same is true for the reverse. If the concentration of a product is increased, more of the reactants will be produced. Next, let's talk about temperature changes. The way a change in temperature affects the equilibrium of a system is dependent on whether the reaction in question is exothermic, meaning it puts out heat, or endothermic, meaning it uses heat. For our purposes, we can think of heat as being either a product or a reactant. In an exothermic reaction, heat is a product, and in an endothermic reaction, heat is a reactant. Now that we've established that, heat changes can be thought of in the same way that concentration changes are. Increasing the temperature of a system is like increasing the concentration of heat, and decreasing the temperature is like decreasing the concentration of heat. Changes in equilibrium follow the same rules as previously outlined. Finally, let's talk about pressure changes. This rule only applies to reactions consisting solely of gases. This is also the only concept for which our scale example doesn't really work. For pressure changes, what matters is the moles. In a chemical equation, the mole-to-mole ratio of the species in the reaction is shown through the coefficients. For pressure changes, it is important to know how many relative moles there are on each side of the reaction. As pressure changes, a system will try its best to keep the pressure somewhat constant. It does this by shifting the equilibrium towards either the side with more moles if the pressure is decreased, or fewer moles if the pressure is increased. These changes help keep the pressure constant. Now, you might be wondering why we should even care about this. Well, there's actually some very practical applications of Le Chatelier's principle, most notable being the manufacturing of chemicals. In processes like the Haber process, for manufacturing ammonia using this reaction between hydrogen and nitrogen, Le Chatelier's principle for temperature and pressure can be used to make the manufacturing as efficient as possible. Since we want to produce ammonia, we want the equilibrium to shift towards the products. This reaction is exothermic, so performing it at a lower temperature will cause the desired shift. In the balanced equation, we can also see that there are 4 moles of gas on the reactant side and 2 on the product side, so increasing the pressure would also produce the shift we want. Therefore, Le Chatelier's principle helps us figure out that for the most efficient manufacturing, we should use low temperature and high pressure, and we'll have all the ammonia we could ever want.